Yes. So, yes. Okay. Good afternoon, everyone. Today we have Marco from originally from Ecuador. Okay, so he did his master's, Bachelor of Science in astronomy, right, in Chile. Then he moved to do his master's in Heidelberg in AGN outflows. Then he's currently doing his PhD with the galaxy evolution and AGN research group, right? Mm-hmm. So today he will present his research on galaxy evolution, insights from the perspective of resolved properties. So Marco, we have the floor.
Thank you.
You're welcome.
Yeah, I will set up a timer just to know that I'm not slow. Can people in the Zoom hear me from here?
Yes.
Yeah, okay, good. Okay, so thank you for the introduction, and thank you for I want to thank the organizers who might be not here in person for making it possible today that I give a talk, and also for the participants today here. All right, so my work in general focuses on active galactic nuclei, but most of the data that I use is related to spatially resolved spectroscopy, which I'm not sure how many of you are very familiar with this, which is why I will give broad overview of what science can we achieve with this and what have we learned so far with this technique. And yes, I will explain also why is it important to understand galaxy evolution in a broader way. And yeah, then I will show you how I actually use this data to understand what is the role of active galactic nuclei in the picture of galaxy evolution. Yeah, so I will not go into the very basics of yeah, I will not go into the very basics of astrophysics, but I just wanted to start with this picture to start a discussion in the introduction. I was in a workshop a couple of weeks ago, and I heard something that I would say it's very, very interesting, which is that 100 years ago, or about 100 years ago, we didn't even know that galaxies exist. At least we didn't know them as we understand them today. So about 100 years ago, we discovered that they are actually extragalactic systems. And before that, so after that, the understanding of the scales of the universe in humanity increased over several orders of magnitudes. So soon after we discovered that these are external objects and they are individual galaxies, we started to create classifications to try to understand them. Suddenly after we discovered that the colors sort of correlate with the morphologies, being the ellipticals in general more redder and the spirals in general more blue. And then with spectroscopy and chemical analysis of galaxies, we started to understand that the redder colors are usually more consistent with older stellar populations and vice versa. And with this, people and scientists can already start asking more deeper questions, such as, do they actually evolve from one side to another? What makes a galaxy stop from having stars? Or do they actually start already with very low star formations? And most of the answers or most of the knowledge that we have about these questions on galaxy evolution comes from a big service, which I will call spatially resolved single fiber spectroscopic service. One of these is the so-called SDSS. Most of you, I believe, have heard about this one, which basically targets about 4 million of galaxies with single fiber spectroscopy, meaning that they look in general at the center of each galaxy, and you basically map the spectra of the inner region or integrate it to try to have a general sense of each galaxy And you can do a lot of good statistics with this. So of course you have a spectrum, and with this you can have distances, star formation rates, stellar population ages, metallicities, meaning what kind of abundances or how abundant are metals or elements higher than hydrogen and helium. You can have velocities, dispersion of gases, and the stellar populations. So what have we learned about this with single fiber spectroscopic methods that target millions of galaxies? And I want to emphasize that I will mostly focus on low-redshift galaxies. So some of the things that we have learned is, for example, trying to characterize which is the most likely ionization source that we observe from galaxies. So each point in this plot is a galaxy, and in the y-axis and the x-axis we have emission and radius, which basically, in a general sense, try to predict from theory. So this line is basically the maximum starburst line, and objects that lay above this line in general are more consistent with galactic activity, which I will briefly describe later. And these galaxies laying below this line are more consistent with regions that have more star formation. But again, each point here is a galaxy. We have also learned that if we put galaxies in a plot, for example, containing star formation rate in the y-axis, I'm not sure if you can read this on the back, and stellar mass in the x-axis, we kind of start to see that there is a trend, at least for galaxies that have high star formation. They seem to follow a tight relation, while there is a group of galaxies that apparently are in a less star forming sequence. So we can learn actually that if we classify galaxies, as I showed before, as star forming, usually the galaxies that are actively star forming are in the region where this sort of correlation is. And this is the so-called star formation in sequence. So we can learn and put constraints on how galaxies that we have actually form stars. And we can already start to ask, okay, well, what makes the galaxies go down in this region, or they even do so? So more things that we have learned are, for example, and again, each point that I showed before is a galaxy. Again, each point here is a galaxy, and we can, this is a so-called mass metallicity relation, where we basically can say that the more massive our galaxy is, the more abundance of higher metals it has. So for example, this is the abundance of oxygen, which is kind of trying to trace metallicity. So we can understand that the more mass the galaxy has, the more events that have created these elements have occurred, and somehow the gases, the metals are retained in the galaxy, and these things are recycled. So we can understand and put constraints in. So with this, we can learn to put constraints in the models of galaxy evolution that we have. And then we can try this and see whether it makes sense, for example, in simulations or in the physics that we try to recover from these objects. So I want to remind you that, of course, this was a very brief introduction of what we have learned with single fiber spectroscopy. And there are more things in general, but I want to emphasize that these things are observing only in the center of the galaxies, but we don't know what happens in the outskirts or in farther regions from the center. So one technique that you could rely on, because many papers, of course, started to see the problem that there are aperture effects. The more far the galaxy is, the larger the aperture that you have over the region that you are averaging in the galaxy. And most of the properties, starting with using studies with long slits, they started to observe that there are gradients actually in the properties of the galaxies. So one way to study this is basically putting a lot of fibers. And this is exactly what the Sloan Digital Sky Survey Mission 4 does, at least for manga, which is one of the projects of the Sloan 4. This is the so-called spatially resolved spectroscopy. And now, instead of having one single fiber for each galaxy, we have many. But of course, this is more expensive. So the limit is on the sample size. Now we have 10,000 galaxies, but there are still other surveys that have this type of data integration, but they are smaller. But this is one of the biggest, if not the biggest survey for doing spatially resolved spectroscopy. Okay, so let's try to update what I just said in the first slides and what happens if we have the optical diagnostics, so the emission and radius that I showed, but for one specific galaxy. And this is exactly what is happening here. Now, now each point here is one different region of the same galaxy. This is observed with muse. So on the left, you have the image of the galaxy. And on the middle, you have basically a plot colored by oxygen. I think oxygen is the green. I don't remember exactly. It's not important. The purple one, I think, is nitrogen, and definitely the one on blue is hydrogen. So basically, you can see that the central regions, which are the purple ones, have, of course, this is a galaxy that is active, and this is selected on purpose to show this behavior. So you can see that in the center, the galaxy is very likely to be ionized by an active nucleus. And then in the outskirts, you have that the galaxy is more dominated by star formation. So you can already see that the galaxy is not only a star-forming galaxy, or it's not only an AGN, it's not only an outflow, and I will talk about outflows later. Here is another example, of course, chosen on purpose to have these features, where in the very center you have an active nucleus. So you can recreate some of the plots that I showed in the beginning. So this is, again, trying to, so I know this plot is now very short, but the y-axis shows you the star formation rate divided by the stellar mass. So basically the specific star formation rate. And we see that for spirals, which are at the bottom plots, this behaves usually flat. You can forget about the blue one. So each different color here traces or bins galaxies according to a specific range of mass. And the blue one, according to the author, is basically trying to suggest that maybe galaxies that are below 9.5 or 10 to the 9.5 stellar masses, basically dwarf galaxies, are probably not reaching the stage of equilibrium of the evolution. But at least for the galaxies that have more than 10 to the 9.5 and that are actively forming stars, or in general spirals, have flat profiles. So when you remember the plot of star formation rate versus stellar mass, the star-forming galaxies form this tight correlation. And this is exactly what we are looking at here. And that slope is not changing. And it's conserved also spatially. So we can already see that these relations hold also with spatially resolved information. And we see that ellipticals here, for example, have suppressed star formation in the center. And there is still some ongoing star formation in the outskirts. So it is very interesting to use this kind of data. It tells you more information about galaxies and how they are actually evolving. So for example, here, you can already see that maybe the regions, this is a plot that I will show later, but the regions around the central regions are suppressed first. And this tells you, this is evidence of an inside-out growth scenario of the evolution of galaxies. Yes. We also have here the mass metallicity relation, but now it uses every position of galaxies that had a star-forming region in this plot, in the so-called DBT diagram that I showed. And basically, these are the contours of all the predicted abundances of oxygen as a function of stellar mass surface density. And you can see that the contours tell you that when you try to study these scatter in a spatially resolved fashion, the scaling relations in general also hold. And just to show some radial profiles in general, you can see here in the left plot that the stellar mass surface density in general decreases with distance, which kind of makes sense. This is what you would expect. And most of the radial profiles, at least in this study from Sanchez 2020, most of the results that I've been showing from spatially resolved spectroscopy are from a review from Sanchez. Yes, and basically most of the radial profiles show a decrease from the center. Also, if we look at the radial profiles of tracer of metallicity, we can also see that this decreases to some extent from the center. And if we look at the look-back time of the setup or the built-up mass at different annuli, so each color here now represents the assembled of mass in galaxies at different annuli. So yellow colors are more in the central regions. This red one is at 1 effective radius, at 1.7, and so on. So the bluer, the more far you get from the galaxy. And you can see that the central regions have formed their mass faster as a function of look-back times. So this is evidence also for local downsizing. Basically, you don't have only downsizing globally between different galaxies, but also within galaxies. All right, so you can learn a lot of things with spatially resolved spectroscopy. So some takeaway messages here are that galaxies, and I quote this directly from this review, which is basically the galaxies can never be considered just as a star-forming region, just as an AGN, or just as an outfit. The scaling relations, most of them have resolved counterparts. There's still some evidence to unmantle there, but most of them have resolved counterparts. And ionization is better when you have information, especially information, to understand how the different ionizing sources can contribute to the continuum in the galaxy. And yes, some of the sort of things I already said in the last slides. So yes, I will do a mini break here to just say a few things that were said already at the beginning. And you can also, I invite you also to interrupt me if you have questions from what I said before. But I will just take 2 minutes here and then continue to another topic. So basically, my home country is Ecuador, and I did school. I was there until my high school, and then I moved to Chile, to Universidad Andrés Bello. I was supposed to be an architect, but I just didn't know that you could study astrophysics. So I learned that in Chile, and then I just started to study astrophysics. My supervisor was studying gravitationally lensed quasars, and then I discovered active galaxies. And I later did a small internship in Chile that led me more into the regime of AGN, and then I applied to a master in Heidelberg. This is the city. It's a very beautiful place, very student-friendly. So the heart of the city is the university. And yes, later I started my PhD there at the Galena Research Group, which is led by Dominica. Here in the center, this is our research group. And yes, now slowly coming back to science, my main interests are AGN feedback and what is its role in galaxy evolution. So we are going to start with AGN in the next slides. Then I also have interests on resolved winds and outflows in galaxies, and I extremely like to create graphical user interfaces for science and data analysis, which I like to highlight because I think we need these kind of things. Right. So why should we study active galaxies? And I'm not sure how familiar is the public with this, but I will not go into big details, maybe on broader details. So we know today, and I believe the consensus is, as far as I understand from the literature, that most massive galaxies host supermassive black holes in their centers. And if we pick at a random galaxy at low redshifts, we will basically see that most of them have a supermassive black hole that is today dormant. By the way, all of this is AI generated. So the thing is that this black hole is, even if it's dormant, is supermassive. So it must have had set up its mass in the past. If you take its current accretion rate and you go back in time, there's no way it have grown that big. So there must have been an event or many events during the evolution of a galaxy where the black hole was actively accreting matter and actively growing. And this is exactly what we understand, or what we call an active nucleus, the process over which the black hole is actively growing and accreting matter. And this was speculated like 30 or 40 years ago, if I'm not very wrong, maybe even earlier. And small calculations of the energy release of the accretion scenario here suggests that even if a small amount of energy gets released into the galaxy, it should have a significant effect on it. All right, so some of the sort of evidence that we have for of galaxy evolution between supermassive black holes growth and the host galaxies is, for example, a so-called M-sigma relation. Basically, we have that the mass, the bigger the mass of the central supermassive black hole is, the faster the velocity dispersion of the central components are moving, which kind of tells you, okay, actually the region where the supermassive black hole gravitational field is efficient is orders of magnitude smaller as compared from the region that we are measuring this velocity dispersion. So there's no way that these things, that the supermassive black hole is somehow increasing immediately the velocity dispersion of the stars, but some sort of coevolution in the history of the galaxy could lead to this correlation. Also, we have evidence from the look back time star formation history. If we look at the star formation rate density, which is the black line, we see that it peaks at around redshift 2. And if we study the black hole accretion rate density, which is a sort of a tracer of the AGN activity, we see in the red line that it also peaks at about redshift 2. So could be a coincidence, or it could be that both scenarios need each other to some extent, supporting the evidence of AGN influence galaxy evolution and vice versa. Also, I believe, I'm not expert in simulations, but most simulations today, I believe they need some sort of feedback to actually produce the amount of stars that we see today at low redshifts. So here we have basically the baryon to stars comparison efficiency. So how efficient are halos in converting their mass into stars versus the mass of the halo. And in blue you have, or in greenish light blue, you have the shaded regions of the observed data. So this is what we know from observations. And in the gray line here, we see basically a simulation where we have no sort of feedback at all. and we overpredict the production of stars in galaxies. If we include star formation feedback, for example, from supernovas, we can explain better the lower end of the halo mass distribution, but we overpredict still the larger mass side. And the only way in which this can be better constrained or look as our observations is when we include both stellar and AGN feedback. I will stop this discussion. I'm not very expert on how they actually do this, but we have there's also support from the simulations. So how does this coevolution actually happen? One way in which we can study this is through the evidence of outflows or AGN winds. So we see in galaxies that are consistent with activity that there are winds ejected from the central regions where this activity is happening. Of course, the more luminous, it's easier to see it, and these effects are more they are seen in a greater extent. But when the galaxies have less luminosities, it is a little bit harder to understand this, which is why today it's not understood whether the effect of this gas ejecta is negative, where in this case it suppresses or stops star formation, or whether it's positive, enhancing and what's the word in English? Influencing in a positive way star formation. So what is important is which of these two mechanisms, because there's evidence for the two of them. The important one, or the important understanding is which of these two in average and over cosmic times is actually winning or more efficient. Okay. So just to wrap things up, I have mentioned this key evidence of what we understand as a possible way to know that there's a coevolution between supermassive black holes and their host galaxies. I showed the sigma relation. I showed that there's a link of the star formation rate density and the black hole accretion rate density over cosmic times. And that in general, introducing the AGN feedback helps simulations to reproduce better what we observe in the universe. I emphasize that in the next slides, I will mostly focus on ionized gas kinematics. This is how we study AGN winds, basically from the O3 emission line, in my case, for ionized gas. And yes, so before actually speaking about ionized gas kinematics, I want to mention a few more stuff. So I want to emphasize, as I was saying in the first minutes, that we need IFU, especially for this kind of study with active galaxies, because most of the activity happens in the center. And in order to understand how this spread through the host galaxy, we need spatial information. Again, this is why I am using MANGA. And this is some already data from MANGA. Basically, in each different spatial position, you have a different spectra. You can see that from the center compared to the outskirts, the signal to noise decrease. In the center, I have chosen this galaxy on purpose, of course. So you have that the center is dominated by an additional Gaussian component, which we do not claim that it's an outflow, but we usually are more cautious and interpret it as a kinematic disturbance. So we can create maps of this parameter and many other parameters, but basically in my study, I create maps of this parameter, and we call this the W80 parameter, which in the literature, the definition is basically the width over which the 80% of the emission line flux is. I will simply call it during this talk velocity width. It's the velocity width of the complex component of the O3 emission line. So you can create maps of this, and this was supposed to appear later. The things that you see here are basically the contours that you can use to create a rated profile of these maps. So I will mostly use, remember that we have 10,000 galaxies from manga, so I will mostly use results from the first part of my of the results that I will show. I will mostly be focusing on results using these radial profiles and stacking them together to compare different galaxy populations. So which galaxy populations? Of course, galaxies that have activity, but there's an additional problem. So every time we want to select or try to say this galaxy is an AGN, so we are going to use it in the study, we find that not every AGN is as good as others into shining up each of the spectral windows that we want to use to classify it. And also we have the multi-phase component. So there's evidence that AGN are episodic, given the meaning that they do not only happen once in a galaxy. So another AI-generated picture, we can decide to use many different techniques to classify activity in galaxies, but there is evidence that the different techniques that you use to classify them do not capture the same AGN populations. So this can tell us a little bit about the different trigger mechanisms, maybe, and also a possible connection to its evolutionary cycle. So I'm showing some evidence here. This is from Ryan Hickox, 29, basically showing 3 different ways to select AGN from the same region of the sky. And they show that the bolometric luminosity, which is a direct measurement of indirect measurement of accretion in the active nucleus, they find that the radio ones are the less luminous in bolometric luminosities and the more massive in terms of the mass of their supermassive black holes. So the way you select them can affect the sample that you are studying. So you have to be careful when you try to study AGN. Also, the host galaxy property changes. So these are just the AGN properties, or the properties related somehow to the supermassive black hole. And these are properties of the galaxy where the black hole is, or the activity is. So this is the star formation rate versus stellar mass. Again, this is what I showed you in the first plots. This is the so-called star formation main sequence. And we see that AGN selected through optical are usually below this main sequence. When you select them in radio, this is again the main sequence, the one in black. Sorry for the change of plots. It's from different papers. But the galaxies that are radio selected, that are AGN selected from radio, they lay a little bit even more below this main sequence. So also the hosts properties change with the way in which you decide to select AGN. And last but not least, ignore the red points. This is molecular gas. So for ionized gas, we see a sort of correlation between the volumetric luminosity of the AGN and the maximum, I think in this case, for this paper, it was actually a velocity width. So the velocity width of the ionized gas scales with the volumetric luminosity of the AGN, which is also important to take into account because this can generate differences on the width that you're trying to study from the kinematics. So basically, I'm trying to emphasize that different selection techniques can find AGN that have different properties and that are in different host galaxies. And the response, the response of the ionized gas kinematics to these different selection techniques could maybe tell us about the driving mechanisms, and maybe there's a connection also to the AGN duty cycles. Okay, so how in my study the AGN are selected? We are using 5 different selection techniques. I don't put the 5th one because it's a small sample and it's X-ray and then it messes up the Venn diagram, but basically we have mid-infrared, broad lines, optical, and radio. And just emphasizing from which studies I have taken this. This is from Comerford, Fu et al., broadline catalog. We did a BPT classification, a BPT Yes, oversimplification, but it's basically spatially resolved BPT. And then we did a radio classification on a paper that we published this year. So this is again the so-called BPT diagram that I showed in the beginning, where in general, as I said, you will find regions consistent with star formation below this line, and above this line regions that might be more related to activity from the supermassive black hole. And if we put the AGN that are not classified by optical, but all of the other ones, they are everywhere, which highlights a little bit already the impact of selection techniques when you try to study activity. Okay, yes. So let's move to the next slide. Yes. The main points here is that we want to understand where the wave of selection can change the kinematics that you see from the different AGN populations. And we are combining this with spatially resolved spectroscopy. Okay, so we, in the paper that we published this year, we studied the differences in the kinematics of AGN that were classified by just optical selection techniques and by just radio selection techniques. So I will call sample A the just optically selected, basically an optical sample combining broadline and optical, removing radio. I combine broadline and optical because both, when matched in properties, they present the same radar profiles of the velocity width. And the sample B is basically the same, but the opposite, the opposite in the sense that we are only selecting galaxies classified as AGN from radio, but removing the ones from optical. If we compare the galaxies that are in sample A, which is only optical, to non-AGN, so my non-AGN sample is basically all the galaxies removing everything that I classified by any method as an AGN. And we see that if we match this sample by stellar mass, redshift, and morphology, the sample of optical still can be more kinematically perturbed than non-AGN. But I showed you in a couple of slides ago that there's a relation, or with some scatter, that the volumetric luminosity, which could be traced by the O3 emission, scales with the velocity width. So if we match the velocity width also for the creation of the non-AGN control sample, we see that optical selected AGN, when removing the radio selected AGN, have less, or I mean, have almost the same velocity width profiles when compared to non-AGN. Yeah, so this doesn't happen with the radio sample, and some speculation is that maybe there might be a population of obscured AGN still in the non-AGN sample, or this could be evidence also of or for fossil outflows, which basically mean that outflows can still be ongoing after the AGN turned off, and we might be seeing a population of these mixed in the non-AGN sample. But now let's compare AGN to AGN. So sample A, again, optically selected versus sample B, radio selected.
This control sample is, you remove the radio ones.
All the types of AGN that I classify with mid-infrared, radio, optical, X-rays, and broadlines.
No, I mean, when they get closer to each other, what did you eliminate from the non-AGN?
All the galaxies that were classified as AGN in any selection technique. So I have a non-AGN sample,
yeah,
and I have samples of AGN classified by optical, by radio,
okay,
by mid-infrared, and so on. And I remove these ones from the sample of the non-AGN. So I'm stacking.
Well, how did you define the non-AGN in the first place?
I just take all the galaxies in manga, and I remove the galaxies that were classified as an AGN. This is how
By optical. Now, I don't understand how it, I miss it, how they got closer together.
Okay.
What happened here, from here to there?
I matched also the O3 luminosity. Yeah.
Oh, you match them?
I also used created a control sample for making them to have the same O3 luminosities.
That's the control.
Yes, the
But
AGN.
but then you are, because the O3 luminosity comes from the AGN, so
Mhm.
if you match the O3 luminosity, I don't know, you took some AGN out.
First performing
Why
galaxy,
are-
or it's performing galaxy. You can also meet all three with it must be a.
No,
really-
because
yeah,
it's a
powerful.
way to make, more O3 luminosity is to have an AGN.
Mhm.
If you make them to have the same O3 luminosity as the control, you are eliminating the AGN, I think.
Or it is
From
what
the
you
sample A.
mentioned that it might be obscured AGN that you are not catching with any of these classifications.
Because this only happens if I remove the radio ones. And in the radio ones, we don't see this behavior. There's still an excess on the radio ones. This is the only way I point out the optical here.
Okay, I can talk with you
Okay.
later. I did understand very well.
Okay.
To make the O3, because it's a way to differentiate them if you have an AGN and non AGN.
Yeah,
At least in the optical.
okay.
To have more O3, usually it's the AGN. So you are taking out the AGN. I know.
We are indeed removing the most luminous AGN, yes, yes.
Okay.
Yeah. Okay, if we compare AGN to AGN, wait. Yes, so sample B is the radio one and sample A is the black one, which is pure optical. And when we compare them with each other, the sample B, which is the pure radio, has always more velocity widths at all annuli when compared to pure optical sample A. So some speculation here. So radio selection techniques are sensitive to having more emission and widths. These two samples are matched. The control sample is also created with stellar mass and O3 luminosity. And this could be related to the fact that outflows can drive shocks, which could also generate radio diffuse emission, which could be sensitive to our radio selection techniques. And also we could have unresolved radio structures. Yeah, so we speculate that pure selected AGN could also be in a higher evolutionary AGN stage, because this difference is also up to higher effective radius, and it could be that there must have been more events to create perturbations up to higher effective radius. And indirectly said, this study doesn't use kinematics, but they study AGN selected from radio and compared it to a control sample, and they also find evidence of them being in a higher evolutionary stage of galaxy evolution. So yeah, I want to quickly show one of the main reasons why I'm here, which is a serendipitous discovery, not very serendipitous, but sort of. I discovered that galaxies, forget about star forming first, galaxies with radio gigahertz detections have more perturbed kinematics than galaxies that do not have radio detections. Why am I using star forming galaxies now? Because it's easier to make interpretations, or I think it's easier if you don't have an AGN to start with. So I created a sample of gigahertz detected star forming galaxies and non-gigahertz detected star forming galaxies, and they have the gigahertz detected have more kinematics. But of course, we have the bias of non-detection. Of course, the more massive galaxies would be easier to detect in radio. So we use LOFAR, lower frequency radio survey, and we see that. Oh no. So yeah, this is basically the non-detected and the gigahertz detected. 5 minutes, okay. So the gigahertz detected, when I see the luminosity of the 144 megahertz from LOFAR and compare it to the gigahertz detection or luminosity, we see a tight relation. So I am going to use this to correct for the non-detection biases by creating a control sample that has the same 144 megahertz luminosities and the same stellar mass. So basically, I create a twin sample, star-forming galaxies detected in gigahertz versus star-forming galaxies not detected in gigahertz. They have the same stellar masses, the same redshift, and the same luminosities in megahertz, and they still have increased kinematics at all annuli. So this is basically the radar profile of the W80 velocity wave. And there are more differences also. So this is the D4000 radar profile trying to estimate age. And apparently they are a little bit more younger in the central regions and a little bit more older in the outskirts. The BPT, so the distance from the maximum starburst line of the BPT, which is at 0, this tells you that the star-forming galaxies that have radio detections are more closer to this line. And using some data from the megacubes from the Riefeld et al. 2023, we see that the extinction is greater in the central regions of these gigahertz detected star-forming galaxies. And the story goes on. Also, there is an increase of featureless continuum. We have removed every AGN from this sample. And there's an increase of featureless continuum in the gigahertz detected galaxies. And there is also, and this is what I also discovered recently when I was in Santa Maria the last week. Through some discussion with Roger Marr, we discovered also that the intermediate age populations of stars has a larger percentage of stars in the central regions. So I don't know when this is going to end, in 3 minutes. I also see that the megahertz morphology of radio is more compact in the galaxies that have gigahertz detections. So there are two scenarios where, there's no reason to believe, or maybe yes, maybe I could be biased, but I wouldn't expect at the beginning that a gigahertz detection means that it has more kinematics. And then it also meant that it has more extinction. And then it also meant that they are more compact in the megahertz. So there's a story, an interpretation to be waiting to be interpreted. So we have two theories. It could be that galaxies that are gigahertz detected have a population or a greater population of supernova remnants, increasing the velocity dispersion of the gas. But somehow this is concentrated more in the center. It could also be, this is very preliminary, it could also be that we would be detecting galaxies that are a little bit more evolved and have had more AGN events. Maybe this is not very careful, but this is why I'm trying to understand what all this data means. So yeah, AGNs or supernovas. So to wrap things up, I have showed the importance of using integral field spectroscopy for understanding galaxy evolution. I showed that the radio selection techniques, when you try to understand AGN, find AGN with more perturbed kinematics when you control for host galaxy properties and AGN properties. And I have found a sample of star-forming galaxies that, when have radio detections, they have more perturbed kinematics. This also happens when I only use AGN versus AGN, and when I only use composite galaxies versus composite non-detected radio galaxies. Okay, so with this I finish my talk. Thank you for hearing.
So if you have any questions for Marco, feel free to ask.
Just a comment on your scenario. I think that you actually might have a combination of the things. Because usually what you find in AGN is that AGN activity is related to nuclear star formation also. So if it is a supernova causing this radio emission, I would expect that you also find it on AGN, because AGN also have nuclear star formation, so we can see that it's together. So I would like to say that it's explanation 2. a large population of supernova remnants in the center. That is also common in AGN because nuclear activity is also correlated with nuclear star formation.
Yes, yes. So actually, there's a paper from Rogerio this year that I didn't read in detail. I just Roger Mark just told me about this when we were discussing this, and I read it a little bit fast. But they find that AGN, when compared to controls, have more intermediates that have a great percentage of intermediate young stellar masses, which might be the ones that are exploding in supernovas, pushing the gas to make AGN triggering.
So, also AGN tend to have like nuclear reservoirs of molecular gas. So it will also explain larger dust amounts if you have like nuclear star formation, lots of molecular gas in the center, so you have a larger extinction.
So we have measurements of the Y colors, and the gigahertz detected are more red in the Y colors. In the W2 minus W3 and W1 minus W2.
So what I think you have is kind of like you managed to find a population of galaxies that have like that recently had a nuclear star formation episode. Some have AGN, some do not, and that's what you find with the control galaxies that also have like star kinematics.
So
it might be that AGN is buried up.
We might have another resolution to find it. Yes.
Ujero wrote some comments there. Check on the other side. See.
More metals to the SM. I see more metals. Yes. I didn't show the plots. That's not loss of. I will read it now. So the intermediate age population will expel more metals to the ISM, thus high reddening, which is what I showed also. Also, the mass loss of this population may be feeding the AGN, so it can be regulating activation or deactivation.
I have a question. I participated in that paper by Comerform of the radio galaxies. And I realized that I had a discussion with it. Because when you look at the radio AGN, you show it that the morphology, they are mostly early type galaxies, right? They are the older population, I think. They are in below the main.
Yes.
So just arguing that in those cases, when you have a radio AGN, it's because if you have a early type galaxy, you have little gas there, then the accretion is going to be the ADAF mode. Do you know about this mode of accretion? It's radiatively inefficient accretion flow. And these accretion flows are the ones that are better to collimate radio jets. Okay? So in radio galaxies, many of them that don't have too much gas, they are going to have these accretion flows that have some funnels. In the accretion flow makes a funnel, and this funnel collimates the radio jet. So my point is that it's a distant population, and it's like maybe old AGN. Is that what you were arguing, that they are in the evolution?
A later evolutionary stage, yes.
Because a later stage that you don't have too much accretion anymore, so you just have very little accretion, and they tend to be radio producers.
Yes.
So it's something like that.
More question.
So I think it's a mixture of populations that you are having. Right?
In this case.
It's a mixture because you have the optical population of AGN that are more close to the main sequence of formation by a little bit. And then you have these very early type galaxies that have little gas. and then they have the radio. So they are, although you say that you have some radio also.
You are speaking now about not these results, but the comparison between optical and radio.
Radio, yeah,
Yeah.
because you are saying that the radio have more kinematic,
Yes, yes.
more
yes.
disturbance, but they are not the same as the O3 emitters, the strong O3 emitters, or are they? Because some of them are not, right?
So I am matching for stellar mass, for O3 luminosities, for
Oh,
morphology,
okay, also,
for morphology and for redshift. Yes.
so all the samples have the same.
Yes, yes, yes. There are slight differences in the morphology because it's very hard to make the control and the sample then gets to 10 galaxies. But for this one, I managed to control for these parameters.
And so then the excess of radio emitting early type galaxies go away. Because you won't find many of those that are of correlation.
Yeah, but I remember that sample from Copenhagen.
Yeah,
A
yeah,
lot
no.
of ones that
Yeah.
didn't have too much of.
I'm
Yeah,
not
yeah.
using the common for
No, not-
radio. No,
Okay,
I had
so-
to create my own.
You created, but you used the radio sources there.
I used the mid-infrared from Comerford.
Oh, okay, not so much the radio.
I didn't use the radio because
Oh, okay, because I, in that sample, I realized that many were like early type galaxies that have little gas. They have.
I can explain why I didn't use it this one, but I did my own sample. And my selection of radio agent is basically using what star formation rate we would have from gigahertz luminosities compared to H alpha, and throwing a line here at 0.5 vex away from the 1-to-1 relation, if both predictors of star formation rate would be the same. So this is my radio sample. The ones that are still gray are the ones that didn't have enough signal to noise to study the ionized plasma.
So your sample is the galaxy.
It's the yellow one, yes. Orange. Yeah.
Mm.
Yeah.
Yeah, so you lose a lot of early type galaxies, right? Because you won't find the alpha emission there.
Yes.
So they're not selected.
But still, I try to mask for morphology.
Yeah, and also then maybe, I don't know if you found a pair for each and everyone.
Probably not.
Yeah, so you then throw away more early type galaxies. Yeah.
Yeah.
And there are one thing that I want to mention that you maybe talk a bit louder already, like,
But not important. I mean, yes, we went to have lunch, but not.
you didn't talk about the work.
No.
Did I show you work?
No.
So she has to show you the work. Well, you're going to stay there then.
Until Thursday,
Until Thursday.
including
Okay.
Thursday.
Okay, so she'll have time to show them. Because one thing that we are finding that is interesting is not only have a sample of contour, a sample of agent, but match each agent to their contours, because, well, we match it like the type of the galaxy, each galaxy has its contour. Not all galaxies are contours to all AGN.
Yeah,
So we match each AGN to their two contours,
Yes.
and they have the same mass, the same inclination, the same morphological type,
So
same redshift.
You don't match the distribution, you match galaxy by
Galaxy
galaxy.
by galaxy.
Yeah. So I'm trying to be using the same method here for the star forming ones compared to the non-detected and the radio detected. So yeah, I'm using also this method. Okay, but not for the other one.
Not for them.
No, not for the radio selected
okay.
AGN versus optical.
Okay.
So now I started to do this.
Do this,
Be
yeah.
even more careful, but at least for this paper.
Okay.
Yeah.
Yeah, I think it's important because sometimes we don't see too much difference, and then when you match exactly the ones that are close, then you see a bigger difference.
Yes, I agree with this.
So it's like you have
One has to be very careful.
a galaxy in the off state and the on state. So you are comparing on and on. But I think we can talk later and learn a lot of.
Coffee break.
Huh?
You can check it at coffee break.
Oh, okay.
Okay, someone has more questions?
Do you plan to also do this comparison for the other selection methods like infrared,
Yes.
X-ray?
Yes, and I just want to brag about. Let me see if I can find this quick. What do I call this? Don't remember. Okay, maybe I can show this later then. But I have a graphical user interface where you can choose how strict you want to be with the control sample. You choose 2 samples of galaxies and you start to pop up all the plots that you would like to see. This of course only works for manga, for my data, but yeah, if we are going to go for it, maybe I can show this later, but to individual people. But so here I can. It's very small words. Okay. So I will put more things here, but for example, here the name is horrible, but this is the star formation rate. The star forming galaxies that have radio detections. These are the non-radio detected, and I will of course put more samples here. It's really easy to do, and I can put a radar profile of the W80 again. It's very different. The green one is the radio detected. And then you can select how you want to match these things. So let's say stellar mass and star formation rates. This is a tolerance parameter that decides how strict it wants to be in the matching. And this is how important your parameter is. So if I put this and I now update, it's still different. It's still different. And you can see a scatter plot of the stellar masses. And they are very similar. This is a 1-to-1 scatter plot. And this is for star formation rates. Okay, a little bit offset, but we can increase the importance then on the star formation, update, and then it gets more closer. And the differences are still there. So I can do this for many different ways of classifications of galaxies to see what parameters actually influence others. And I can add also importance. I don't know, ages. We have a lot of parameters here. But yes, I plan to do this for more galaxy populations.
Yeah, very nice.
And also show more.
First time I see something like that.
Yeah, so I can compare many results from the megacubes also in real time and update the plots accordingly to the controls each time. Yeah.
So it's for each one galaxy, I mean, it's not understand.
Yes. So here it's showing it's very bad contrast here, but this is the stellar mass of the star forming detected by radio, and this is the stellar mass of the star forming not detected. The scatter is a 1-to-1 basically, and the line shows the perfect scenario, right? And the same for star formation rate. And then
this is for the whole down or whole sample.
The whole sample of star forming galaxies that have radio detections compared to the ones that don't have radio detections. So the galaxies that have non-radio detections, they are the ones that are controlled in general to match in the properties that I select as important. So I just created this yesterday, and I still haven't played with this. Not that I just learned how to do this in one day. I have been doing this for a lot of time, and I finally created this version to be able to discuss things better and in real time here to understand the data. So I think it's good if we have a couple of rounds of discussion. Yeah. So.
Thank you.
In the future, we intend to look at